What's up, y'all? How's it going? We've got another banger by Will from Dragline Dynamics. What's up, y'all? How's it going? We've got another banger by Will from Dragline Dynamics. What's up? Okay, we gotta turn off my my stream. Oh no, wait, mute that. Okay, everything's muted. I was listening to myself like, oh, this is all good. I hope y'all can hear me all right. Yeah, I guess it has a dark mode. I don't know. So we're just going to be working on some CAD here. And we're going to, you know what I'm going to do? We're going to watch some of my old videos in the background. I also turn the heat down a little bit to see if my computer will not overheat. Got a clever rig for that, although we're still clocking 65 degrees. But as long as you don't get close to 70, that would be nice. I put like an auxiliary fan over there, so if you're hearing background noise, that's what that is. Yeah. Let's see here. Okay, Patreon, Instagram, YouTube, we're all good. We're all good. All right, I hope you guys can hear me okay. I've got no feedback. What's up, guys? What's up? It's good to see everybody. All right, all right. We're gonna go back in time. Is what we're gonna do. We are gonna go back in time. And you know what? I think I've got to just arrange these windows as best I can, you know? Because the streaming thing is tricky to get the hang of. Like, I need to be able to see what I see. And you guys need to be able to see what I see. So it's tricky. It's very tricky. We're going to go back in time. We're going to be watching, we're going to be cringing together to the complete saga of web shooter science. That's what we're going to do. And I'm going to put, I'm going to pop out chat here. And just let me know. Just let me know how it's going. Maybe I can pop out Instagram too here. Oh, Jonathan's on the cruise. What's up, guys? All right, we got the Instagram chat. We got the YouTube chat. We got everything going on here. Crazy stuff. Bro, what is this dude crying about? Okay. Change from just over 7 meters. Ooh, we got to rewind. All right. Let me know if y'all can hear this okay.
Add the perfect touch.
Sorry about the ads. I can't afford YouTube Premium.
To sweet holiday memories. Simply say yes to simple.
Yeah, just let me know how it's going. This might be the last time I stream on Instagram, by the way. I'm thinking of just doing YouTube.
An old cowboy went riding out one
Skip this. I don't need that. Handsome he was.
What's that? Oh, let's start with a joke.
I'm not funny.
Okay. A lot of people ask me why I wear the mask, and I say like, oh, it's so I can be a symbol, and you know, but really it's just that I can look down at my teleprompter and no one knows that I'm doing it.
Can't do that anymore.
So, yeah.
Want
Want to know who my favorite superhero is? Green Arrow. I'm just kidding. It's Spider-Man, obviously. And you want to know the one thing that's always fascinated me about Spider-Man? His superpowers aren't all that super. Now by that, I don't mean he never does things that ordinary people couldn't do. I mean, throughout his fictional appearances, we've seen him jump off of buildings unscathed.
Full of the exaggerated swagger of a black teen.
We've seen him sustain injuries that could easily kill the average person. And we've seen him maintain actual personal relationships despite having way too much going on in his life. Not to mention the number of times his secret identity should have been revealed but somehow wasn't. No. What I mean to say is if you take each of his powers at face value and you evaluate its physical improbability, none of them really hold a candle to some of the other soups out there. I mean, web shooting? It's just a simple liquid to solid transition. There's tons of real physical or chemical reactions that could create these same effects. Wall crawling, we've had engineers help humans climb even the smoothest walls for a while. And some humans don't even need the help. Super
So
agility,
dope.
I mean, have you seen
Love
what
Simone
Biles has
Biles.
been up to? Never mind the millions of
goodness.
gymnasts and traceurs around the globe who repeatedly recreate Spidey's moves. A quick disclaimer, some of them get seriously injured. Or worse. Super strength? Obviously, the strength Spidey demonstrates is simply unachievable, but there are some pretty strong people out there. Not to mention that exoskeleton innovation is continuously improving. Now, Spidey sense is really a question mark, but given that it's not ever super well defined, you could draw a comparison to night vision or even simple motion detectors. And this is different from superheroes like Batman or Iron Man, who are supposed to be simply human, but still appear to be superhuman in some circumstances. And this is different from heroes like Captain America and Black Panther, whose only real superpower is super strength, and it's really not well defined in fiction if they are superhuman or just peak human. No, Spidey is unique. His superpowers are actually superpowers. He's got stuff coming out of his hands, and a theme song.
Yeah.
The whole shebang. But it's not at the level of, I don't know, super speed.
I cooked.
Shooting lasers
I
out of
cooked
your
with
eyes
this
or
video.
manipulating probabilities or whatever. His superpowers are a bit, I don't know, I don't want to say mundane, but just nowhere near as godlike as some of the other superheroes. And you wonder why this is, you know, it sort of contributes to the relatability of the character. If you look at the context of a lot of the other characters out there, Peter Parker and Miles Morales aren't so much superhumans as they are secretly above average at a few things. And I like to think we all feel like we have our thing that we can do that other people don't know about, and then one day we just drop it on them like, guess what, motherfucker, I make a mean chocolate cake and it's really impressive.
Calm
Yeah,
down.
it's like that. I mean, Spider-Man is basically like a quarantine mom making sourdough, except he doesn't tell absolutely everybody about it. Now wait a minute, let me zero in on one of those powers I
Whoa.
mentioned earlier. Yeah. Web
That's a bit
shooters.
much, buddy.
What did I say about that? It's just a simple liquid to solid transition. There's tons of real physical or chemical reactions that could create these same effects. Now hold on. Is it really that simple? I feel
Nope.
like I'll need my lab coat for this. Alright, that's better. Now, of course, there are tons of real physical or chemical reactions that could create the effect of web shooters. I mean, nylon synthesis, melt-blown thermoplastics, solvent evaporation, to name a few. But which one is best? You guys can't tell, but I'm raising one of my eyebrows. Now, I would say, as far as what
Haha,
we've seen in
Vsauce.
Spider-Man fiction, web shooters have two basic uses, which I like to call grappling and catching. Now at this point you might be asking, excuse me Mr. Amazing, but what about a web shooter that doesn't use fluid? What about a simple grappling gun mounted on the wrist? To which I say, get the hell out of here. No, I'm just kidding, you can stay. For now. It's true, these web shooters, which I call solid line web shooters, are also a viable option, and many people have actually tried making them, including yours truly. These basically just consist of a simple projectile propulsion mechanism, whether it be electromagnetic or pressurized gas powered,
something happen to the
explosive
YouTube
propellant
stream?
powered, or just spring powered.
Hold on. Something happened to the YouTube stream? I gotta find out. Did it start a new one? No, it didn't. We're still good. Sorry, I was like, man, no one's responding for a while, but that's fine. I guess not that many people are watching. It's not a big deal.
What we have seen unfold before our eyes in
Did it start a new one? No, it didn't. We're still good. Shut up. Okay, sorry about that, y'all. I've got PTSD from a couple streams ago. All right, let's get back to it.
With some sort of line attached. These are generally advantageous for the
Built
range
IRL,
they achieve and the high tension
GOAT.
of pre-manufactured
He's
solid
great.
line can sustain, especially if you're
I
using
wish I
something
knew
like
him.
Kevlar. In case it wasn't obvious, these web shooters are pretty much good for grappling only, unless you're including net guns in this category, which are obviously for catching. But I haven't seen a wrist-mounted version. Actually, that's a good idea. I better write that down.
I should get on that.
And even when grappling, once you shoot your projectile, it's shot. What do you do then? Oh, you want to shoot another one? Tough. You forgot to design a real system or a cartridge system, and now you're falling from the sky. Now, I've done both reels and cartridges, and I will say it's still a huge delay between shots. This is partly why I designed my conveyor belt web shooter, which is more of a proof of concept than anything else at the moment. And another thing I feel like no one brings up, not even me, is I can't hold on to this tiny line. And yes, I'm calling this tiny, you'll see why later. And if I make it any bigger, I can't store it at all. But apart from that, the main thing is that these solid line web shooters don't show the versatility we'd expect from Spidey's web shooters in fiction.
That's what we're working on right now. That's what we're working on right fucking now.
While fluid web shooters have not shown the same capability for grappling as solid line web shooters have shown, the truth is the technology is closer than it's ever been. And it gets closer all the time. I mean, sure, this line is pretty weak, but it's an achievement in and of itself to just make a line out of liquid instantaneously. The fact is, fluid web shooters have the potential to be good at both grappling and catching. Now, in the vast majority of cases, a fluid web shooter will be utilizing the chemistry of polymers. Due to these specific class of chemicals' relative strength and unique ability to melt and dissolve, or even the polymerization reaction itself. Now, there might be a reason for this. Spider silk in nature is technically a polymer. Polymers are long chains of molecules, and due to weaker
17.
secondary bonds between the chains, they can tangle and shape themselves to reach very specific structures, leading to very specific properties. Spider silk has the insane tensile strength and elasticity it has, not because of the amino acids in the peptide chain, but because the hydrogen bonds in the chain cause segments of the protein to form helices and spirals, leading to elasticity, and very crystalline ordered sheets, leading to strength. Now, while nature has had millions of years to evolve the structure of spider silk and make it one of the best performing materials in existence, we've had just under 60 years since Spidey came into existence to imagine a real-life web fluid. So you know what? Just cut me some slack, okay? I mean, nature had a head start. The benefit of even having the opportunity to alter properties of the fluid using chemistry cannot be understated. This means that there are potentially limitless web fluids, as opposed to choosing between a Kevlar and a polyester line at the hardware store. Oftentimes, the concept of a polymer blend may be of use. This is similar to the concept of alloying in metals to increase strength, but also to alter other properties. Mixing different polymers together may give the resulting line unique properties. Science aside, let's face it, we're all drawn to the idea of a fluid web shooter a hell of a lot more than the line web shooters. That's because it's the method actually used by Spidey in fiction. He's always talking about web fluid this, web fluid that. That mystery of how the liquid suddenly forms into a strong solid line is a fascinating question for all of us. And that's a mystery we can solve together. So let's lay out key aspects that web shooters need to achieve. A liquid to solid transition, high velocity, and an adhesive-cohesive balance. Let's start with the liquid to solid transition. We've already touched on this a bit. Web shooters don't run on diesel. This transition requires that some liquid source, easily stored and easily dispensed, turns into a solid material at the nozzle of the web shooter. If you classify the web shooter into two domains, you essentially have the inside and the outside. Such that we can say the substance within the inside domain must be a liquid, and the substance within the outside domain must be a solid. So we can think about the different environmental properties in these domains that can make this possible. For instance, pressure, temperature, mixing states, or rheological effects.
Oh no, an ad!
Year price guarantee.
Man, another commercial!
Alright, discussion time. What did we learn? Did we learn anything? By the way, I'm going to do 100 push-ups if I get 20 super chats, so just saying. Yep. Yep. That web fluid problem is so cool. It's just like I talk to my material science friends and I'm just like, oh, I wish that I had done material science because they're working on some cool stuff. Um, yeah, I've got a friend working on like nanocellulose fibers from I think it's from flax, I think. It's natural fibers that are really strong, almost as much as spider silk, which of course is another natural fiber, but more mass producible, right? But again, like most strong materials, oh, it's back.
A useful prop.
Like most strong materials, it's not really soluble in anything, as far as I know. So, you know.
Many of the web shooters I presented on my channel, as well as the famous silly string toy, use this effect. With a pressure-driven evaporation solidification process, a propellant is used that can exist in more than one phase at the ambient temperature of operation. When it is pressurized within the inside domain, it is what is known as a saturated liquid-vapor mixture. Some of it is liquid, and some of it is vapor. When both of these phases are present, the vapor exerts a constant pressure, known as the vapor pressure, no matter what the quality or how much of each phase is present. The exertion of the vapor pressure is what allows this substance to be a propellant. The propellant exists purely as a vapor in the outside domain, when both the temperature and pressure are ambient. If some of the substance within the inside domain is able to escape to the outside domain, some of the liquid phase on the inside domain will evaporate to mix with the vapor phase, maintaining a constant vapor pressure for the inside domain. The solidification comes into play when the propellant also acts as a solvent in its liquid phase. It dissolves the other ingredients within the web shooter. To put that simply, if one of the other ingredients is a polymer, then bing bang boom, as soon as that liquid solution reaches the outside domain, then bing bang boom, that vapor evaporates away, and you're left with a big ol' solid polymer, hopefully with web-like properties. This is the method that I and others have used for the most part in the last several years, with the fluid usually involving the solvent propellant, tetrafluoroethane, and the polymer, polymethyl methacrylate. You can check many tutorials for that stuff on my channel, but people still ask. Temperature is a property I've seen applied in two basic ways, both of which also require phase transitions. The first way is still evaporation, only this time it's temperature driven. Say you still have that liquid solution of a polymer on the inside domain, except the solvent is no longer a propellant, it can only exist in its liquid phase at ambient temperature. If you don't add some sort of temperature change to the outside domain, then that solvent is never going to evaporate and you're just going to end up with a weird squirt gun. But if you're able to heat the outside domain above the solvent's boiling point, then that solid polymer is going to be left behind in all its web-like glory. Now, when comparing the two methods of evaporation, they each have their advantages and disadvantages. Firstly, propellant evaporation is passive. It requires no power source. It's simply a system trying to reach equilibrium. The heated evaporation, well, that heat has to come from somewhere, whether it be resistance heating, a heat pump, a gasoline engine, something that actively introduces energy into the system. On the other hand, propellants that have required properties are almost overwhelmingly volatile organic compounds that are harmful to the environment or to the human body. There are a few chemicals where you can skirt around the environmental issue, but it's still an issue. With heated evaporation, your solvent could be arguably anything, as everything has a boiling point. It could be water, for instance, which is pretty much harmless, and there are water-soluble polymers. Now, apart from evaporation, temperature can be employed in another way that I haven't seen until recently. In this case, the liquid to solid transition is a process many of us are already familiar with. Freezing. Not as in like involving ice, as in the opposite of melting. So you have a polymer that's solid at room temperature. How do you store it as a liquid? You melt it down and store it at high temperature. Thus, the outside domain being colder allows the web fluid to solidify. This is something I've only seen from a channel called Joel Creates, with his hot glue web shooter.
This was crazy.
However, I can only imagine the amount of power that is required to store a whole tank
This
of
was
molten thermoplastic.
crazy.
And I left a comment asking Joel if this is a problem, but
Crazy
he
dangerous.
didn't reply.
Yeah, Max Brain Devices also has it, but I don't think he stores it at high temperature.
Journey with
This is all
childhood
many
cancer
years old at this point,
comes
by
at
the
you
way.
in
This is like
waves.
4 years old at this
Every
point.
day we wake up knowing that our 2-year-old has cancer. It's tough to get through.
The tumor.
I feel heartless muting these ads, but they are ads, and that's just the name of the game. But yeah, you should give to St. Jude's if you can.
Now, what about mixing? This generally involves chemical polymerization reactions, which is the forming of bonds between molecules to form polymer chains. Two chemicals mixing can usually be enough to introduce this reaction, though some happen quicker than others. I mean, I love quick curing epoxy as much as the next guy, but 5 minutes for a web shooter to become a web is enough time for the lizard to bite your head off. I want to add a disclaimer here, as I am about to talk about dangerous chemicals, so please don't close the video after I mention something cool and go try it yourself. You might end up severely hurt in the most horrible ways if you don't take the proper precautions. A quicker polymerization that a lot of people have brought to my attention, and yes guys, I am aware of it, and if I see it in my comments again, I swear I will just... Yes, I am talking about nylon synthesis. Now, nylon is one of the strongest polymers out there, and it's usually synthesized with two chemicals mixing. One is adipoyl chloride and one is hexamethylene diamine. Gosh, that's a mouthful. These two chemicals are commonly positioned at different layers in a container, with the boundary between them forming nylon, which is continually drawn or spun out of the solution and collected as a fiber. So these chemicals aren't some that you would mix like you would epoxy, but I would be interested to see what would happen if you synthesize nylon through a static mixer. What would come out the other end? This definitely has to be tested in a proper laboratory because both adipoyl chloride and hexamethylene diamine are dangerous as shit, pardon my French.
Bro.
I'm talking serious
Relax.
burns and severe irritation dangerous as French, and
Relax.
that's not something I think anybody wants. So if you're not a chemist with adequate protection and ventilation like this dude, don't experiment with this, and definitely don't go shooting dangerous chemicals at high velocities, and definitely don't do it in public. Other fast methods of chemical solidification don't seem to be so much polymerization reactions as they are cross-linking reactions, where polymer chains already exist, but they are in liquid form, either in solution or they just exist in a liquid state at room temperature. Examples include the classic slime experiment, where borax is added to polyvinyl acetate glue and the polymer chains are cross-linked. Recently, another spidery inventor, the human spider, and I looked into a process that is used to make artificial caviar called spherification. This involves introducing an aqueous solution of sodium alginate to calcium ions, which replace the sodium ions, creating bonds between alginate chains. Keep in mind these cross-linking bonds are not covalent, so they are easier to break, and they are easier to break than the covalent bonds in epoxy or nylon. All of these chemical mixing procedures now require an additional domain for the web shooter. The outside is the same, but you now require two insides, if you want to call them A and B, where the two parts that need to be mixed are kept separately. Only just before they reach the outside should the contents of A and B be mixed, so that the web shooter doesn't clog up with polymerized or cross-linked material. Now this is obviously a disadvantage as it requires additional hardware, 2 canisters, 2 valves, and possibly more, making for a bigger web shooter. That brings us to rheological effects, which can be interesting, but the web spinning applications presented here are highly theoretical. Now,
I'm busy.
Rheology is the study of the flow of matter, but the term is usually applied to fluid studies. This includes concepts like viscosity, which we colloquially describe as a liquid being thicker or thinner. Viscosity is a constant for what are known as Newtonian fluids because they follow Newton's law of viscosity. That viscosity is the ratio of the shear stress applied on a fluid to the amount that its velocity changes over the direction perpendicular to the velocity.
They love to steal our
Which basically
shit
tells you how much the
because
fluid
we
is
come up
responding
with
to the applied
original
stress.
things.
If the velocity changes a lot as a result of the applied stress, then the fluid has low viscosity. If you're trying to get liquid to flow or stir and you're applying a lot of stress but nothing much is happening, then the fluid by both mathematical and logical reasoning has a high viscosity. Viscosity can also be understood as the internal friction of a fluid, when the molecules have a hard time slipping past each other. Only some fluids are actually truly Newtonian, like water for instance, but most can be approximated as such. For non-Newtonian fluids, whose mathematical laws I won't go over here, viscosity is not constant. Either the viscosity increases when more stress is applied, or it decreases when more stress is applied. These two basic types of non-Newtonian fluids are called shear thickening and shear thinning fluids respectively, for both the type of stress that the fluids experience and for the effect that the stress has on the viscosity. Some shear thickening fluids exhibit this property so dramatically such that they act as a solid when external forces are applied to the surface of the fluid, like with the classic mixture of cornstarch and water. The opposite effect can be described for shear thinning fluids like ketchup, when the fluid won't even budge until some sort of external stress is applied, like tapping or shaking. Of course, You could never really tell how solid the fluid is within the container when no stress is applied, as measuring that would require applying some kind of stress. So that's interesting. So basically, the two domains of the web shooter, the inside and the outside, could be characterized by the type of stress the fluid is experiencing. And you want the web fluid to act liquid on the inside and to act solid on the outside. Now, I've done this briefly many years ago with a safe shear thinning fluid composed of xanthan gum and water that was able to shoot out as if it were water, but was also able to adhere to the side of a surface without dripping all the way to the bottom, as if it had solidified. Now, of course, it's easy to doubt the practical applications
It hadn't
of something like
solidified.
that.
That's the thing.
But the only alternative at this point is shear thickening fluid, and you couldn't build a web out of that because it's probably going to be liquid when stationary, and you couldn't shoot it out as the shear stress applied to the fluid during propulsion would solidify it before it even left the shooter. So neither is really something that you want to take with you when you're crime fighting. But just imagine for a second, a fluid that acts solid when tensile stress is applied, as opposed to shear stress. Now, I'm not really an expert in this area, but I know this is a very strange idea, as I've never heard of fluids experiencing tensile stress, as the molecules only have trouble sliding past each other. They aren't really difficult to separate from one another. That's like solid stick. But if it were possible, it could potentially be something that you could hang from and shoot out of the nozzle. Basically, you need some type of matter that doesn't really exist, a fluid that basically acts as though it knows exactly what you want it to do. So finally, we have our sort of insane multi-dimensional pro and con list for liquid to solid transition approaches. Now, as you can see, there are more cons than pros in all approaches, but I don't know, maybe I just designed it like that to make a point. I guess I'm a pessimist. Well, let me know in the comments if you think one of these cons isn't actually a big deal, and maybe I'll turn my mood around. Also, please let me know if there's an approach that you think has not been covered here, and I'll be sure to check it out and discuss it in a future video.
Life is more legal than you think, and LegalZoom is here to help. Whether it's registering...
Blah, blah, blah. Blah, blah, blah. Oh no, the goal is running out. I'm not going to be able to do my 100 push-ups. What am I going to do? Okay, so if this ends up being 5 volts, then this... Well, wait a minute here. Wait. Confused. That's pulling down. Why am I so confused? Oh, wait, what? Did I design this wrong? No way. Wow, I designed this pretty incorrectly. That's pretty stupid. That might explain some of the weird force sensing resistor that I've been having. Huh. Interesting. Very interesting. I feel like I've looked at this before. Am I going crazy? Okay, it's back.
Everything much more complicated. We've already discussed briefly the production of nylon, where the polymer created is very, very strong, but has to be manually pulled from the chemical bath and wound around a spool as a fiber. This method of synthesis would not work for web shooters. Actually, this is a very common production method for materials like this. Oftentimes, a special dye called a spinneret, crazy, yes I know, like a spider, wow, is used to force whatever solution is being used through tiny holes to create the fiber. And a variety of methods are used to solidify it. But this is a very, very, very slow process, not really the behavior we want. The same thing goes for the deposition of viscous fluids that are intended to cure, usually into elastomers, which is just a fancy name for stretchy polymers like silicone or polyurethane. An example of this is the silicone caulk that you would use to seal in your shower or bathtub. The properties of this material are decent and could be considered web-like, but with a viscosity that high, there's no way you'll ever shoot that to a range of more than a couple inches, let alone across a room.
Okay.
Now, range and exit velocity are related in a very simple way. If you've ever taken a physics class, you would know this. Any massive projectile
Did I
under the
really
influence
do
of gravity,
this
whether it
so
be a ball or
stupidly?
a feather or a particle of web fluid, follows a parabolic trajectory. Now, assuming there are no other forces present, like drag or surface tension, which are good assumptions for small, solid objects. Now, when we look at the definitely spherical Earth very closely, the ground looks flat, and that's the sort of range we're most likely going to be using web shooters in, unless you get some sort of cosmic web shooter. Gravity will always act towards the center of the Earth, which in the scale is a direction that presents itself as always downward. Our coordinate system directions, X and Y, will be used
I feel
to
like I'm
differentiate between the
unhinged
horizontal and vertical directions.
making
Since
this video. What am I talking about, dude? What am I talking about? People seem to like it. This was back in the day. I like to sneak flat Earth stuff into videos just because I was so baffled by how anyone could think that was the case. And I was really trying to understand it and also trying to come up with arguments against it. So I'm like sneaking in like, yeah, was I 22? Yeah, I was 22 when I made this video. That's right.
Gravity only acts downward, it will only affect the vertical velocity of the projectile, accelerating it towards the ground.
Damn, how could
The
I do
horizontal
this so
velocity
wrong?
remains
That's
constant,
crazy.
and the parabolic trajectory results.
This should be...
The range
just
is
fix it
usually
right now.
measured as the horizontal coordinate at which the
Because I'll need to
projectile's
fix it
vertical
eventually.
coordinate is 0, or when it hits the ground. The x-axis intercept, if you want to call it that. If you're firing the projectile horizontally, you can find the range by first finding the time it takes for the ball to hit the ground, which is only dependent on the initial y component of velocity and the gravitational acceleration and the height at which it is thrown. Then you will find how far the ball will be able to go horizontally during this amount of time.
This is
which you
correct,
can find
what I'm
by
doing right now.
multiplying the horizontal component of the velocity by the time to impact. From the simulation you see here, we can gather that there are many ways to increase the range of a projectile, by either increasing the vertical height at which it was launched, or increasing the exit angle, but we don't always have unlimited height, and the angle increase only helps up to a certain point, until the projectile motion becomes more like an upward throw. What we can see is that increasing the exit velocity is always beneficial to the range. Of course, we won't always be aiming our web shooters at ground targets, actually almost never, and we would much rather hit the thing we're pointing at, right? I mean, as hard as gravity makes that. So a much
What
more
happened?
realistic
Why did
way
this
to
turn
evaluate
pink?
The range would be to define a tolerance for how far away the projectile hits its intended target, which is something that the exit angle defines. Oh yeah, we are sharpshooters, baby. A target allowance. If you
Did
wanna call
I
it
move
that.
on to the second part
Increasing the
already?
target
I
allowance-
think I did. Yeah, the liquid to solid transition was the first part. We'll watch the second part maybe in a bit, maybe another time. Who knows? Who knows? No, we got no viewers on Instagram. That's fun. How's the YouTube looking? One watching. 610, what's good, buddy? Yeah, we're gonna go into fluid dynamics next. That's what's going on next. But I don't know if I really want to watch. I'm worried. I mean, I did check with a bunch of people who are experts, but I did check to see if my fluid dynamics understanding at that time, which was while I was taking Mech Engineering 520, which is Advanced Fluid Mechanics at Michigan. That's while I was doing that. I can't believe I got this pull-up resistor wrong. So that means I'm going to need to figure out a way to do this with what I have. And so instead of having a pull-up resistor, what I had in this design was a bias resistor, and that sucks. I don't know why I did that. I'm an idiot. Let me try to figure this out here. So I have a pulled down resistor on one side, and then on the other side a direct connection to analog 0. What was I thinking? I was obviously not thinking. So what do we got here? If I have this, if I add another pull-up resistor, no, this is crazy. Like I'm gonna need like a high pull-up resistor. This is so dumb. Why would I do this? So there's an input pull-up resistor that I can have for there's one digital sensor I have, and there's going to be one analog sensor I have. Though maybe I should just replace it. Oh, it should be. It kind of has to be the force sensor, unfortunately, for the operation of this device. So we need the pull-up resistor, and I think yeah. So I should try to make that one. This is crazy. Okay, so this is what I have here. I can't believe I screwed this up so bad. Interesting. Okay. Well, we'll figure it out. It means that I'm going to have to update the circuit board. Okay, so we're going to need like if this is 10K and we need an input pull up here. God, why did I use such massive resistors? Input pull up to 3.3 volts, and this is like a switch. All right. I can't believe this. I cannot believe how cooked this is, actually. Okay. So first of all, I want to know QT pi internal pull up resistors. I don't need to know about the I2C. This might, I'm not using CircuitPython. Stop. No, I didn't overestimate the current. I just used the wrong circuit diagram is what I did, which is really stupid. But so I guess like I can look at this in iCircuit. Okay. Now this is my fun voltage charging circuit. Better save that. Okay. Make a new one. But I just need to know, like, if I put QT pi. Well, I just need to know about the SAMD21 chip. Let's look at the data sheet. How's my computer temperature doing? Because I'm really cold. Oh my god, how is it so hot? What is going on? It doesn't feel that hot. I wonder what's happening. And that computer is also seemingly doing okay. Ow! Like, I don't think there's that much lag. Like, I could be wrong, but okay. So we need to know the input pull-up to be able to fix this, or have some hope of fixing this. internal pull. There's something. Okay. So the internal pull-up resistor. It might have to do with the impedance. Okay. Well, it also has internal pull down. That's interesting. If it has internal pull down, I could. That's something that I could potentially do, actually. Okay, so we need to map this out together. Get rid of this. This is going to be fun, guys. I'm excited. I'm excited. Because we've got to solve a problem. Okay, we've got to solve a problem. So, yes, 610 remembers our digital electronics tutoring sessions about transistors, MOSFET transistors. And they have several different regions of behavior. Got to pull out that textbook again. I'm glad you're done with that class. Let's see. I'm going to save this as problem solver. All right. So here's the problem. On my... I'm going to close the window because I'm starting to get way too cold. No, I don't want this. On my... So we have a ground. We have a resistor. $10K. Okay, and we have a... Let's just call it a... I guess we can call it just a like a gauge or something like that. Okay. I'm going to zoom in a little bit here. Okay. So what do we got? This is that, and then this is that. Like literally, like this is what I have. So it's kind of crazy that, like, if I do a potentiometer here, I feel like this doesn't make any sense, right? Because there's no voltage source, you know? And I think like what I'm trying to do here is the input, like, man, I miss LT Spice, I swear to God. This would be like the A0, right? Okay. So this is the A0 voltage right here. So I have this elsewhere in the board as well. And it still kind of works, but I'm suspicious it's because like there is a kind of weak voltage source on the chip already. Like the chip can be modeled possibly like I don't know, if there's input impedance for I guess this would be like output impedance, right? Yeah, because I found that it still works, which is why I didn't see this soon enough. So okay. So as a matter of fact, this one is 4.7 ohms. And also I'm thinking that there will be, instead of a variable resistor here, there will be a switch. Right, okay. So the thing is, oh no wait, this is 4.7 kilo ohms. Right, okay. So first of all, I haven't looked at this data sheet super in depth. But if they don't give me something in terms of ohms, I'm going to be really annoyed. Bus impedance. This is super in depth, of course. It's interesting. Okay, so honestly, I don't know why this worked. But what I'm going to do is I'm going to draw a can I not like make a little draw a rectangle? Like I can't. Okay. And what happens here is like, oh, it's like, oh, this is wrong. This is connected incorrectly. Always forgetting. So like you can see it only moves between like 3 volts and 3.025 volts, which is crazy stupid. I don't know why this, like I didn't spot this. The web has this circuit in it. And I'm like, it's kind of like the FSR is working. I have no idea why. Like this must be, like there must be like, for some reason, I think when a pin is labeled as input, there must be some like high impedance here or something. Because this is essentially what we need. So this wouldn't work for like a digital sensor, you know. So if this was 10K, then it actually kind of works. Not going back to the drawing board. I mean, I will have to eventually. So you see now it changes between 3 and 1, 3.3 and 1. And that might be enough for like to be registered by the circuit board, by the SAMD21. And this one doesn't move very much. Well, that's because this is 10K and this is 10K. So yeah, it must be like higher even. But I'm like, what is going on? Will I be able to do this? So what I should have is not this, but this. The resist, essentially the difference is this resistor here, and then like this resistor should be like a more real thing and not an internal, like not something that I can change, or something that I can, something that I should have built into the board instead of something I'm hoping is inside the IC, which I guess it is, because you can see, no, what is this? The max resistance is 1K? No, this should be like 1000K. Yeah. There. Now it changes. How much current is flowing through here? Yeah, not much. So you see, changing from picovolts, basically 0, to 3.3. This is a voltage divider, okay? And so for here, for a digital sensor, you can see straight up just goes between 3.3 and 0. Just 1 or 0, basically. All right, it's getting really cold, and I got to pee, so take in this, and I'll be right back. Okay. Okay, so here is the deal. I did this wrong in the design, and I think there's some internal resistance that is inside the chip that I can't really explain, that is kind of saving it for me, but I don't really want to rely on that anymore. So these are essentially no longer like I basically designed these as output pins, right? Like I designed these. I intended for these to be input pins, but clearly I messed up and they're like output pins. So basically what I have instead, and it's kind of dumb because what am I, I shouldn't, that's really stupid because I don't need an LED that has a series resistor that's this high. Like that's pretty stupid. Um, and so, and voila. See how dim that is? Because it's not a lot of current going through with 4.7 kilo ohms in series. So that's dumb, but that's clearly what I had in my head when I was doing this. So that's what it should be. But what I do have, there are other pins that I have access to. And we have the SCL and SDA pins here that are accessible with I2C. And so what I think I'm going to do is, first of all, I want to check we need the other information. Look at the pinout here. Okay, so do they have any information about the pull-up? Oh, they say. Perfect. Good. Now we got that out of the way. There is no pull-up on this pin by default. Yeah. Okay, so we can add these pull-ups manually. We also, of course, have these pins here. But I'd rather just use this because then I just need the one connector. We have if we go to the circuit diagram. Thanks, mother. Mother. I mean brother. Jesus Christ. Pretend I didn't say that. Okay, SDA, SCL, 3.3 volts, ground. SCL, 3.3 volts, ground. So this is the connector that I want to use. But these two pins, SDA and SCL, they don't have a pull-up option on the SAMD21 chip. So I have to add those manually. Okay. Great. Great. So that's what I'll use. That's what I will use. And if we go, that means that I will have access to those 4. Okay, so that means that if I'm looking at this like 8-pin connector that I'm thinking of sticking in this device here, 1, 2, 3, 4, 5, 6, 7, 8. We've got the 2 motors. one on one side. I should just put that on the far side and that on the other far side, because those are the farthest things apart. It should be motor A1, motor A2, and on this side, motor B1, motor B2, and in the middle, what are we going to have in the middle? We're going to have first the FSR here. Wait. Why are there only, did I misread this? Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8. So what is the problem here? Is it because, so that's the limit switch. Limit switch, 2 motors, that sensor. Oh, no, there's 10. Yep, there's 10 wires. Okay, so I need a 10-pin connector instead. Great. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that means motor B1, motor B2. So probably that means I'm running out of room here, but if I extend this, probably extend this by 2.51. I think I still have space. And this one, 2.51. That is kind of eating into it there, but I can move it this way. Hey, that's great. Honestly, eat your cereal 7032. The math and physics part, in my opinion, this is biased to me because like once you get to like PhD level, that's like basically what you're doing when you're doing robotics. I think that's a very important part. You already now have the ability to create models for your robot. So what I would recommend is start. I think the main thing about robots is the fact that they have to move around. So, so you need to learn about motor control, probably, is what I would do, or just control theory in general. Resources are tricky because I got this in school, but I mean, I don't have my textbooks on this one. Wonder if I can. So if we look at PID control explained, okay, so these are the kinds of things that you want to look into. So I want to zoom in here. I can't zoom in. Okay. Okay, so what we're seeing here is YSP. This is what's called your set point. Okay. This is summed with your inverse. Not your inverse. Your negative of what you measure. So basically, you're taking the what you want, you're subtracting what you measure, and this E that you get out here, right, is your error. Okay. So it's basically how far off you are from where you want to be. Like this could be like the position of a leg, could be something like temperature, could be something like velocity, could be anything, anything that is controllable. And PID controller, or any controller, right? This is just your standard like control diagram. Anything can go in place of this PID, but PID is the most basic form of control that they'll teach you. And this outputs a signal or some action U, right? And the U is the input to your process or your system or your plant or whatever you want to call it. And the output is the thing that you want to control. So it's this control loop here, is what they call it. And this signal U for a PID controller, which stands for proportional integral derivative, takes this form. So you said you're already experienced in math and physics, so this should be pretty simple for you to understand. You can see here the proportional part is taking the error and multiplying it by a constant. That's all it is, just a simple gain. That's what they call it, just a gain. The integral takes the integral of the error, so it's basically summing up all the errors that you've had so far. And what you get is essentially a measurement of like how well you've been doing. It's hard to like, it's the cumulative total error. That's what they write it here. Take the cumulative total error and multiply it by a constant, Ki. And you multiply that by, you multiply that by Ki. Then you have the derivative term. You multiply that by the derivative of the error. So that's basically how fast the error is changing, right? Now I forget exactly. I think these gains, they all serve sort of a different purpose. Like you can have a standard just proportional control. So that would be like if you like get rid of this stuff over here and you just have this. That's a very simple controller. Like it works sometimes. A lot of times in robotics, they'll just use PD control, for instance. Essentially, proportional control essentially gets you like close to your set point. When you add derivative control, it allows you to get to your set point much faster. When you add integral control, that will eliminate what's called the steady state error. So that's like once your controller is done acting, you might have still some error, even though it's done acting. And that's a result of the system behavior, you know. But once you add your integral control, you get rid of that steady state error. So there are probably some YouTube videos about this as well. So what do we have here? So this is just proportional, I think. Is that what they're saying? Yeah. Yeah, so this is just proportional, right? You get kind of close to your set point, but it doesn't always work super well. Sometimes there's oscillations. Not great. When you use integral control, you see this still has some steady state error and still some oscillation. This one works pretty well. Gets to that set point. So here's some other examples, I guess, of integral control. Is that right? Yeah, this is PI control, so it's just P and I. You can't really do it without the P, I think. Okay, then derivative control. So you add derivative control, and what you see is you still get some oscillations, but they are decreasing in value. But that means you need to select the P, the I, and the D gains so that the system works properly. And you can do that If you know like a model of your system, control theory, basically says like, if you know what this process is mathematically, then you can work backwards to figure out what your ideal PID gains are. And the same thing goes for we'll just call it, let's just look up LQR, for another more advanced but now pretty standard control algorithm called linear quadratic regulator, which works for well-defined linear systems. So any continuous time linear system can be defined with this equation here, x dot equals ax plus bu, where x is the state and u is the input. And the feedback control law is essentially this right here, in this case for LQR. And then it's about what is k, right? You need to figure out what k is. And there are these equations that you can solve called the discrete, the Riccati equations essentially. But it depends if you have like a discrete system or an infinite horizon system or continuous time. Like there's different equations you can solve for the different types of systems here. But solving those equations will give you what k will lead to the best result for your system. Now, best in this case is defined by a quadratic cost function. So you can define this yourself with the coefficients f, q, r, and n. I've typically only seen it with q and r. I think that's the typical, but I guess you can have other ones as well to be more general. But yeah, this is sort of the thing that you want to look into when learning how to design robots, is essentially the question of defining the model of your process, right? And then figuring out what controller, what function that takes your error and gives you what you want to put into your process, the voltage on the motors or whatever you're working with. If it's pneumatic robots, it could be something like pressure, for instance. Yeah, so that's essentially what I would look into if you already have a foundation in math and physics, but you want to look into how to build robots. This is the math side of that. And I don't know, like to get from this to hardware might be a hop, skip, and a jump. I kind of did all of that I worked on all of that at the same time. So it's not super it's not super clear to me if you want to do hardware first or do this stuff first. But you can play around with Arduinos, and there's all sorts of tutorials on that. I think what's missing for most people's education and where you can be really unique is understanding this stuff while having a good hardware background. That's what I think. Okay. Yes, I was in the middle of moving this. That's right. Okay, so this fits pretty perfectly right in the middle here. And this is that SPI right here. So I might as well put that right there. So that looks like what does that look like? I have that here. Sorry for rambling so much, guys. Welcome. We are working on my cable shooter, and I'm trying to stay focused even though you guys are giving me such a good time with such great questions. So this one is ground, 3 volts, SCL, and SDA. So for me, that'll be so. No, that doesn't exactly work. But it kind of does. It kind of does. Let's see here. Where would I rather put that stuff? Okay, so it's ground, then 3 volts, and then let's call it 5 and 4. So we need somewhere, let's see, I think there's space. Space for resistors. Definitely. So we should definitely do that. The question of what the cable shooter attaches to right now is not relevant. That could be anything. Okay. The main innovation here is the actual shooting of the cable. But right now I've got a projectile with a magnet. It's very simple. But there's all sorts of plans in the works for more advanced things. Remote control grappling hook is something that I've been working on for a long time, but that also requires a heavy amount of mechanical innovation. And that's going to take a while for me to get that right. That's for sure. And I don't have a lot of time. I just don't have a lot of time. So ground 3 volt, pin 5, pin 4, and so this is going to be the other side of that. Let's just draw it this way. So pretty soon I'm going to need to sign off here. I'll give a cutoff at like 9:20. I'll give you guys 14 minutes. How long you been watching, my man? Yeah, I used to do that all the time, and I'll get back to it. Yeah, it's just not super pressing right now. I think where a lot of people go wrong is they have ideas for liquid to solid, and then they don't have the proper hardware to get that to work, because that's kind of huge, and a lot of people don't even think about that. Yeah, we were just talking about the whole video. Like literally, we just watched that earlier in the stream. My whole entire video about my, everything you need to know. Like you should watch this if you want to know some real shit. I made this back in 2021. Very underappreciated video, but this is 1 hour of science that will amaze and astonish. A1, A2. Okay, and so this one. There. And this one will be the ground. Ground should be in the middle, I think. No, ground should be on either end. You got to watch my old stuff and get up to speed. That's what these guys are. They're all up to speed. Here we go. But we're happy to have you. Welcome. Okay, so this is that one, and then this is going to be the FSR. Okay. Great, that works there. And I'm wondering if this now is okay. So B1, B2, B1, B2, is that it? The limit switch. I forgot about the limit switch. Oh, so there's 3 sensors. Shoot. So if there's 3 sensors, then I might as well use... Then I can cut down on the resistors too. If there's 3 sensors, then I shouldn't use that. If there's 3 sensors, then I shouldn't use this port. I'll have to use the 3 volts and the ground here, but I'll have to use the SPI pins, SCK, MOSI, and MISO. Yeah, they're all analog digital, which is great. We just need... That means that we don't need a resistor. We don't need a pull-up resistor for... Because... Like, these should have internal pull-ups. Let me see. QTPi, do SPI pins have internal pull-up resistors? Okay, but I'm not asking about like using them as SPI pins. I'm wondering about using them as just regular digital inputs or analog inputs either, right? Because they're both. And but I'm not asking about I2C either. So QT pin out. You know what, TCS? I don't want to admit that you're right, but uh, like I don't know why this wouldn't work, honestly. I'm just gonna use it anyway, and if they don't have internal pull-up resistors, it'll just be like it'll probably still work, honestly. So that means that we only need an external pull-up for the analog sensor and not for the digital sensor. Okay, so that means that we're going to use 3 volts, ground, and so let me get this straight. I swear to God, I can't, for some reason, get to a straight answer here. B1, B2. FSR1. 3 volts. Should probably just trying to figure this out if I should. I swear to God. No way did you just say YOLO in Year of Our Lord 2025. That takes me back. I'm from that time, by the way. If I do it this way, then yes, that is 1, 2, 3, 4, 5, 6. That's 10. And that means that on this side, we're going to have this one, no. This one, and this one all be tied down. This one goes to a, well, this one, let's just say this one goes to SCK, this one goes to Mosey, and this one goes to Mizo. And that means that the FSR one will need an external pull-up resistor, 4.7 kilo ohms. And those go to the motor drivers, that's whatever. So this way we need 10. Okay. So I think this is probably a fair way to do it. We're going to use 10. We can use 10 pins. And this gets internal pull-up IP And this gets internal pull-up IP. Okay, great. I'm not gonna ban you, bro. What the oh my god, I wish I could get some more intelligent people in my chat. Cool, I get it. My streams are probably not the most interesting, but, you know, is what it is. Anyway, I hope you guys enjoyed. I'm going to head out because I got to grind on this. This has to be done tonight, and I'm running out of time. So thank you for watching, and I'll see you guys